Yeah, g'day, it's Charlie ZL2CTM. Okay, first up, this is going to be a long video, more than likely. The way I see it is I want to do some more experiments with this mixer using the FFT function on the scope, and just sort of talk about what I'm seeing. There's no structure to this really. I'm just going to have a bit of a chat. As you know, like all my videos are, there's no script here. If you're not interested in this, or me just sort of rambling away, please just switch off now and wait until the next video comes out, which should be on the IF amps. Otherwise, like I say, it's just going to be me having a chat about these mixers here and what I'm seeing. I guess first things first, in terms of the setup here, I've got three mixers. The top one here is the newest double balance mixer using the 1N5711s. We've got the SBL one here, and then we've got an earlier version of a Homebrew DBM, same configuration, but the diodes here are the 1N4148s. Again, matched in the same sort of process as I did up there for the latest build. Now, there's a couple of questions on the theory of operation for this mixer. I don't really want to talk about the theory, and as I tried to say in the comment, I'm no expert in this, and I don't want to come across as an expert. There are some very, very good videos out there on all of this theory, including the double balance mixers. So I would certainly encourage, if people want to get the good rundown of how this works, to go and see those. All I can talk about is what I've done, and as I've said many times, these videos are really just a video log or a diary of what I'm playing with, hopefully with the aim of encouraging others to give it a go. I do want to have a quick chat about the configuration of this. That's the circuit diagram or the schematic of this particular mixer. You can see the diode ring there. It doesn't look like a diode ring here in this configuration, but it is. The reason why I've configured it this way was to try and maximize the distance between the tracks leading to the transformers. So this transformer here goes with this trace and this one, and this transformer goes with this one and this one. And in between those is one fully unused track, where I've used a drill to remove all of the copper material. Now, the reason why I did that, both increasing the distance and removing that copper, is to reduce capacitance. So by reducing the capacitance, we know that capacitive reactance is inversely proportional that is to capacitance. So Xc equals 1 over 2 pi Fc. So if our capacitance was to decrease, our capacitive reactance would increase, so therefore I'm minimizing the likelihood of, I'll call it crosstalk, but leakage is probably a better term, between traces. So that was my my attempt to, like I say, to increase that, to decrease that capacitance in an effort to increase the isolation between traces. The transformers themselves, 10 turns of trifilar wound number 28 wire, quite thin, on an FT37-43 core. The twists per inch, so my thumb's roughly an inch, is roughly 10 turns. And I just had 3 separate wires held in the vise and just used the electric drill to spin that up. And then configured them as per the diagram there, and as people are aware, the dots there signify the phasing. So if you look at a coil, everything at the one end would have the dots, and at the other end would be the non-dots. So in a coil like this, wrapping it around, all the dots would be at one end, and vice versa. Okay, so I think that's all I wanted to cover on that, and why I elected to build it the way I did. Now, what I neglected to say before, with the setup here, there's a whole raft of switches here. Now, my logic there is, for these top switches 1, 2 and 3, it's just a nice, easy and convenient way for me to switch the SIGGEN, which we'll look at in a sec, and the O-scope between the new double balance mixer and the SBL-1. The second lot of switches there are switching in and out 51 ohm resistors between the output ports of those two mixers, depending on which one's been selected and ground. The literature out there is quite adamant that these particular mixers need to be or quite sensitive to being terminated correctly with that 50 ohms. The closest one I've got here is 51 ohms, so close enough. So that's what these bottom switches here are. At the moment the 51 ohm resistor is all in play, so the ports have been terminated with 51 ohms, and then I'm just scoping across that or injecting signals into that. Right, I think that's all I need to say there. So let me just zoom back out again. I'll talk about what I've done on the SIGGEN, and then we'll go and have a look at the scope. So once again on the SIGGEN, I'm using both the outputs. For output number 1 here, I've got it set up for 3 megahertz, just a nice round number which makes it easier when we look on the FFT what's going on. Notion is set up for 100 millivolts RMS as the amplitude for that. On channel number 2, as we pointed out yesterday, or as I said yesterday, 2 options for the VFO frequency. So channel 1 is going to be the RF going into the mixer. Channel 2 is going to be the variable frequency oscillator.
I couldn't find any enabled videos.
Oh, sorry, that was Alexa. I don't know why she'd be saying that.
Alexa app to manage your video
Excuse me.
devices.
Okay. I have no idea what I should say there, but never mind. Channel 2, as I just said, was the local oscillator going into the mixer, and then the mixer is going to be spitting out our intermediate frequency. In this particular case, we want the intermediate frequency to be 9 megahertz. So therefore I've got 2 choices, because we know that the output of our mixer is the sum and difference. So we've got a choice of 3 megahertz plus, sorry, in order to get to 9 megahertz, which is our IF, I can either do subtraction, so our 12 megahertz here minus 3 equals 9, or I can go on the low side of our IF and I can do addition, so I can go 6 megahertz plus 3 megahertz equals 9. In this particular case I'm going to choose the option of having 12 megahertz as our second frequency coming in. So what we should now expect to see coming out of the mixer is the sum and difference. So we're going to see 12 plus 3 equals 15, and we're going to see 12 minus 3 equals 9. So we should see 2 different frequencies coming out. Because it's a double balanced mixer, ideally, we'll turn it back on again, ideally we shouldn't see our 3 megahertz coming out of the IF port, nor should we see our 12 megahertz coming out of the IF port in an ideal world. And I'll compare and contrast the Homebrew mixer with the SBL one, the commercial built one. So I hope that made sense. So at the moment I've got both turned on, and we'll have a look at that in a sec. Right, so spinning across to the oscilloscope. Now I'm not going to move the camera backwards and forwards because more than likely I'm going to make someone seasick. So I think the best I can do there, hopefully that is in focus, is just leave it looking at the scope, and off camera I will tweak, move, fiddle, and we'll see what's going on the scope. So at the moment the scope is set up for a FFT using the maths function. I've slowed down the time base, and just make sure that's still, yeah. Slowed down time base to basically get a picture here where I've got sent up the center frequency. So this line, see the blue claret there, that line there is 10 megahertz, and I've set up the divisions, so these major divisions here, to be 2 megahertz per division. So that's 10 minus 2 equals 8, minus 2 equals 6, and down we go, in the other direction of course, 10, 12, 14, 16. Right, so at the moment I've got the Homebrew double balance mixer set up, and just to explain what we're seeing here, the ones of interest are this peak here and this peak. We talked about our sum and difference frequencies, our F1 and F2. So F1 is 3 megahertz our F2 is 12 megahertz. So we would expect to see 12 minus 3 equals 9, which is this line here. So 10 minus half a division, because it's 2 megs per division, so that equals 9. So that's our desired intermediate frequency that we're going to be passing through the crystal filter. And the sum coming out, so 12 plus 3 equals 15. So 10, 12, 14, half a division equals 15. So there goes our second mixer product coming out of a DBM. That's our sum in this particular case. Interesting that from an amplitude point of view it's slightly different from that one, which is interesting. I won't surmise why that is. Could potentially, no, I don't know, could potentially be inductive reactance, slightly higher frequency, therefore slightly, I don't know. I'm not going to try and guess on that one. Now, what I will do, in a double balance mixer, theoretically we shouldn't be getting out our RF coming in, which is going to be 3 megs. So it's going to be sitting down at 10, 8, 6, 4, 2, so in the middle here. So that little line down there is our incoming RF. For interest's sake now, if I was just to increase the level of the RF coming in, so that's at 100 millivolts, 200 millivolts, 300 millivolts, 4, 5, bang, interesting. So now we're at 500 millivolts and it's increasing big time. So really quite important that we don't, or that I don't, or my takeaway is making sure that you don't have a huge RF level coming in, because as we can see here, it just starts to not be eliminated and finds its way into the output. So I'll go back to 100 millivolts RMS and it's pretty well suppressed. The second one over here is this one here. So again, 10 megahertz is our center, plus 2 equals 12. That there is our VFO. So let me just go to that channel which is there. And if at the moment the SIGGEN is set up for 1.416 volts peak to peak for that variable frequency coming in. I've chosen that one because I'm just emulating the SBL1, which is a 7 dBm device for the VFO drive. So that equates to 1.416 volts peak to peak, close enough. Now if I was to decrease its amplitude, so that's 1.4, 1.3, 1.2, 1.1, you can see that slowly decreasing, now down to 916, but also our two output desired signals are also decreasing. So going back up again, that's 916, that's now up to 1 volt, 1.1, 1.2, 1.3, 1.4, and 5, 6. Interesting here, from about 1.5 onwards, or 1.4 onwards really, very little increase in the actual desired signals coming out, but our carrier continues to increase. So I guess another takeaway is to not go beyond, in this particular case, that 7 dBm drive. And I don't see any great advantages of actually going any less than that. I'm not seeing any huge reductions in anything else. Now when I say anything else, I'm just talking about these other little artifacts here. If I turn off, I'm now going to turn off the RF, and of course nothing comes out except for that little bit of a VFO coming through. I'll turn the RF back on, turn the VFO off, and everything dies away. So if I was now to turn the RF on again, I'm now just cycling the VFO. VFO on, VFO off, VFO on. So a little artifact there, which I don't know if that's a function of the mixer or the scope or something else, but I think it's fair to say it's certainly down in the weeds. What I'll do, I'll just leave the VFO on and I'll leave the RF off, and I'm just going to use the screwdriver here to adjust that potentiometer. As you can see there, that undesired, when I say undesired, we want to suppress that by going through the null is there, back out the other side. So there goes our null there, where in terms of performance point of view, that's the best we're going to get in terms of nulling out that that VFO frequency from making it through the output. Again, remember 10 plus 2 equals 12, which is our VFO. What else I wanted to do on that one there? I think I might do that. No, right. Okay, so let Let me turn on the RF back on again. So now we have our sum and our difference frequencies coming out. Small amount of our VFO and essentially no RF leaking through. Well, leaking is probably, yeah, well, okay, whatever. Okay, so I've tweaked that pot. What I'm going to do now, I'm going to use those two wires that are sticking up, and I'm going to short out that trim pot here. So at the moment the trim pot is in circuit. I've just adjusted that to see, and you saw the amplitude of the VFO, which is here, our local oscillator, on what it looked like on the output. I'm now going to take that essentially out of circuit and short circuit those two windings there directly to earth, which would be the actual circuit diagram for this if you would look at a traditional double balance mixer. Right, let's just put on some glasses, and hopefully without short circuiting anything. There we go. So therefore that's now short circuited and just releasing. It's now back in circuit. And let's do that again. Short circuited, oops, daisy, short circuited and back out of circuit. So what I'm seeing there is I'm seeing a improvement in the level of the desired signals coming out, our sum and difference, and I'm actually also seeing a greater suppression of the unwanted VFO. So that's short-circuited and back off again. So we've seen those two levels go down, and we've seen that undesired VFO slightly go up. So the takeaway for me is, gosh, why would I actually need that? If I'm getting good suppression of that and getting greater output, I might as well just take it out of circuit. So that's one of the takeaways I'm going to do from today's experimenting, is I'm going to remove out of circuit that pot. Right, the next thing I'm going to do, I'm still on the Homebrew mixer. I'm just going to switch out of circuit. 1, 2, 3. I've now just switched out of circuit the 51 ohm resistors. Now they would have been dragging down the output anyway, but I am seeing, what I can see here, an increase in the number of other frequency components here. Now I'm not going to try and second guess what they are, or why they're produced, or the mathematics that's producing those. I'm not going to go there, but I think it's fair to say that in line with the guidance, it's a good idea to have that mixer terminated in 51 ohms, so we'll keep it that way. Right, so at the moment I'm now going to switch across to the SBL1, so just flicking the 2 or the 3 top switches, I can now switch to the SBL1. Interesting enough, those two higher levels there are higher than we saw with the 100 ohm pot in. I did some measurements before, and if I short circuit the 100 ohm pot, I don't come up to exactly the same levels, but I'm not too far off. Interesting enough, I'll turn off the RF, and we can also see now 10 plus 2 equals 12. That's even with the commercial SBL1, we're still seeing a little bit of the VFO, or the local oscillator, same thing, finding its way to the IF port on the output. I'll now turn off the local oscillator, I'm going to call it the VFO, and turn on the RF. And if you, I don't know if you just saw it there, just poking its head up there is the RF. And what I could do, just like I did with the other one, go back to channel 1, and if I was to increase that, that's now 100 millivolts, 2, 3, 4, 5, 6, 7, and as we saw with the not quite the same behavior as the Homebrew mixer. Let me just go back to the other one just for interest's sake. So we'll just nip back to this is now the Homebrew double balance mixer, and increasing its output. And interesting enough, when you get to that sort of, oh, it's actually the same behavior. I'll take that back. I was about to say this one here behaved differently, but I'm going to take that back. Excuse me for just a bit of a ramble there, but this is now back to the SBL1. Yeah, same. Okay, that's good. Rightio, well I'll return that back to 100 millivolts, turn on the local oscillator, and now we're back to seeing our sum and difference as per normal. Interesting. Okay. Okay, so that's enough on that one. Right, so what I'm going to do now, I'm going to go back to the new double balance mixer. So I've now just flicked those 3 switches back, and we're seeing the output of the new double balance mixer, and the 51 ohm resistors are in circuit. I haven't taken those back out. And what I'm going to do now is I'm going to swap over the scope, the RF and the LO across to that old original double balance mixer. So just hold on there. I don't have a fancy switch for that, so I'm going to do it by hand. Hopefully everything stretches across, and one more goes to there. And here we have the output of that old double balance mixer, and if I was to tweet its 100 ohm pot, we should see that again, center is 10, 2 megs per division, so 10 plus 2, this one here growing and decreasing. And my, to compare, comparing and contrasting without actually getting the calculator out and doing any kind of 20 log V1 over V2 to look at any kind of dB differences, but my takeaway from that is compared with the new double balance mixer using the 1N5711s, I've got a reduced output, and my undesired VFO is actually slightly higher, which is of interest. So my takeaway is that certainly the new mixer, this one here, is performing a lot better than the old one, which is great. So more than happy with that. Okie doke, so let me just come on back, and I think in terms of a wrap up that's about all I can think of actually. So just done the comparing and contrasting between the new, the SBL1 and the old. That one's certainly performing better than that one. This one may not be necessarily be as good as this one, but it's pretty good. I'm now going to take out of circuit that 100 ohm pot that's not needed, so that's good. Gives me a little bit more extra output for the same performance, so that's good. And I think that is about that. So thanks very much for putting up with me rambling for 20 odd minutes. Not sure if it was of interest or not, but it's certainly been of interest to me and sort of hammered home a few things. Okay, and it was good certainly to learn how to use that, assuming I'm using it correctly, but certainly helpful. Okay, 73 all, stay safe, and we will see you next time, which should be, fingers crossed, working on the IF amps. We'll see you then. Cheers all.